In this lecture, we are going to cover the topics of integer linear programming problem. If you remember, in the normal linear programming problem, whatever decision variables we considered, the decision variables x, capital X, usually are positive, that is greater than equals 0. That is, they can take the real value, they can take the integer value also. But you may have certain problems where decision variable can take integer values only. Just like suppose your decision variable is how many tables I want to purchase, how many chairs I want to purchase. Something like this way, when decision variable can take only the integer values, in that case the normal LPP will not work, because normal LPP works for the data where the decision variable can take non-negative real values only. So, you have to find out certain other algorithm similar to your simplex method, by which we can say that this can be giving you the integer problem only. So, let us see this one in the integer LPP. So, we are going to cover this integer LPP. Linear programming problem discusses so far whatever we have discussed uses variables which are positive real numbers. But this may not be always true, as I was mentioning. If a variable represents number of chairs, number of books, number of persons, number of vehicles to be find out, in that case this will be integer, not real number. So, in an LPP where all the variables are restricted as integers is known as integer programming problem, or in short we will denote it as IPP. Please note this one, in an LPP when all the variables are restricted to only integers is known as IFP. If some of the variables IPP, if some of the variables are restricted as integers, then we call it as mixed integer programming problem. So, mixed integer programming problem means the variables may be integer or it may be real number, whereas only integer programming problem means the decision variables with which we will work, they will be only integers, they will take only the integer values of the variable. Let us take one standard IPP, that is integer programming problem, which is of the form maximize zx subject to ax equals b, x greater than equals 0 and xj belongs to capital X are integers. Please note this one, x is greater than equals 0, but we are imposing one additional condition, that is xj belongs to some set capital X which are integers. Now, the solution methodology for integer programming problem or IPP. Basically, we use two particular approaches. One is Gomori's cutting plane method and another one is branch and bound method. Gomori's cutting plane method, in this particular method what happens? It was developed by R.E. Gomori, and this method is based on this basic concept, introducing new constraints or cuts to the problem, which removes the non-integer optimal solution, but does not affect the feasible integer solution. So, please note this one, that whenever we have non-integer optimal solution, it removes or it cuts that particular solution, and by which we are doing it, you are introducing a new constraint to the problem. Please note this one, we are adding a new constraint to the problem by which we are removing the non-integer optimal solution, but the solutions which are already integer solution, they will not be affected by this method. So, let us see this one. In this particular method, we first find the optimal solution. In this method, we find the optimal solution of the given IPP by simplex method, discarding the integer condition of the variables. That means, at first what we are doing? We are finding the optimal solution of the integer programming problem by normal simplex method, whatever we have learned earlier. Disregard of integer condition, that means we do not consider now that the decision variables are integers. So, whenever we are solving the integer programming problem by normal simplex method, by removing the integer condition, some situations may arise. The first situation is if the values of all variables are integer in the optimal solution. So, if the values of all variables are integer in the optimal solution, obviously that will imply current solution will be the derived integer solution. The current solution will be the integer solution. Number 2 is otherwise the problem requires some modification. That means, the solution whatever you have obtained, their values of some decision variables are non-integers. So, what we do? We introduce a secondary constraint which we call as Gomori's cut, that reduces some non-integer values, but does not eliminate any feasible integer solution, which I emphasized earlier. So, we are introducing one constraint which is known as Gomori's constraint or Gomori's cut, which basically will remove some non-integer values, but it will not affect the already integer solutions which are feasible. The third is the optimal solution of the modified problem is obtained by the standard algorithm. In this solution, if all the variables are integers, then your procedure stops here. That means, after introducing the new constraint, you are restructuring or recreating your table, and again you are using normal simplex algorithm to solve the problem. And if the solution, if you find that all the variables are integer, that means you have obtained your optimal solution, which is feasible and whose values are integers, values of the decision variables are integers. Then you stop the process. Otherwise, another secondary constraint has to be added to the current IPP and the process will be repeated. That means, you will go on introducing the constraints till you have the values of the decision variables of the basis is a real number, that is non-integer, and you will repeat the process. So, actually what happens? You consider this optimal non-integer solution. Suppose you have Cj, Ck, Cj's are there, C1, C2, Cm. You have the values of y1, y2, ym. Here you have xb, b, cb, b values are there. I have divided into two parts, one is Cm, other values are there 0 to ym plus 1. So, here x1 to xm are the basic variables. Please note this one. Here x1 to xm are basic variables, in this case are basic variables, and remaining n minus m variables, that is xm plus 1 to xn, xm plus 1 to xn are non-basic variables. So, you are assuming this thing, that on this you have the basic variables x1 to xm and remaining n minus m variables, that is xm plus 1 to xn are non-basic variables. We assume that kth basic variable is corresponding to the non-integer value. Kth basic variable corresponds to the non-integer value in the solution. That means, you have the some value x b k, which takes some value like this 0 into x1 plus 0 into x2 plus like that way 1 into xk, you are going on, plus 0 into xm, plus we are writing yk m plus 1 into xm plus 1. Like this way, the last one will be yk comma n into xn. So, we are assuming that kth basic variable in the basis corresponds to the non-integer value, and that we are writing as xbk equals this thing. So, xbk you can write down xbk equals xk plus all other will be 0. So, summation L equals m plus 1 to n ykl xl, and from here you can write down xk equals xbk minus this quantity, summation L equals 1 to m plus 1 to n yk comma l into xl. So, the variable xk is basically non-integer, and which we have written as xbk minus this thing. Now, let xbk, this is equals to ibk plus fbk. It has two components, basically xbk and this ykl. So, I am writing and ykl equals ikl plus f of kl, where ibk and ikl are integer part of xbk and ykl respectively. So, basically each of xbk and ykl you are writing as in terms of integer part plus the fractional part. So, fbk and fkl are the fractional part of xbk and ykl. Since we are assuming that xk is non-integer, so the coefficients here xbk and ykl we are writing in terms of the integer part plus the fractional part like this way, ibk plus fbk, where of course this fbk and fkl, fbk and f of kl both belongs to 0 and 1. Both belongs to 0 and 1. Note this one is the open bracket. So, therefore, from 1 I can write down xk equals, just substituting the values of xbk and ykl equals ibk plus f of bk minus summation L equals m plus 1 to n xl into ikl plus f of kl. This we can write down, and from here I can write down again from this one I can write down fbk equals fbk minus summation L equals m plus 1 to n xl f of kl, xl f of kl, this will be equals to xk minus I of bk minus summation L equals m plus 1 to n xl ikl. Suppose this is equation 2. So, basically just by from the last equation, just taking the elements on the left side or right side, we are writing this one. Now, on the right side of this equation, if you see your xl, your ibk, your ikl, this will be xk, ibk and so here xk, xl, ibk and ial are integer parts. So, RHS up to this one contains the integer part. Therefore, what happens? Since your fbk, that is the fractional part, lies between 0 and 1. So, you can write down summation L equals m plus 1 to n XL f of KL, this will be greater than equals 0, and your FBK minus summation L equals m plus 1 to n f of KL XL, this is less than equals f of BK less than equals 1. So, from using these two conditions, we can write down f of BK minus summation L equals m plus 1 to n f of KL into XL, this should be less than equals 0. Now, this part f of BK summation L equals 1 to m plus 1 to L f of KL, this part is an integer, then it should be either 0. If this part has to be an integer, this should be either 0 or it must be negative. So, then there must have some inequality by which this we can introduce some non-negative Gomorian slack variable to make it equality. That is, I can write down f BK minus summation L equals m plus 1 to n f of KL XL. Since this is negative, so I am writing GK, this is equals 0, where we call it this one, this GK as Gomorian slack variable. This GK we call it as Gomorian slack variable. So that we can write down from here minus of f BK, this is equals minus summation L equals m plus 1 to n f of KL XL plus GK. This constant, this equation 3 is known as, this 3 we call it as Gomorian cutting, plane or Gomorian cutting. This is known as Gomorian cutting. Now, so by this way, as we told earlier, that we will introduce one new variable over here, sorry, one new constraint whenever we have one value of the decision variable is non-integer. So, what would be the equation constant? The constant will be basically this thing, this is less than equals 0, and using Gomorian slack variable we are getting this equation. So, this we will use in this case. Now, your FB quite naturally from this equation, if you try to see, your value of XL will be negative. From here it should be negative. So, once the value of the decision variable is negative, if required we can use dual simplex method to solve the problem. Because if you remember, already we have done in the dual simplex method, if you have the infeasible solution, that is the value of the basic variable is negative, how to convert it into positive by using the dual simplex method. So, that we have done over here. Now, let us see the flowchart for Gomori's pure IPP. So, see, come to the first one at first, because this is coming through the entire thing. You are starting over here, reformulate the integer programming problem in the standard format. That means, make it into less than equals type constraint, and the problem should be maximization problem. Number 2 is ignore integer restrictions and solve the IPP as usual by simplex method. As I told you earlier, ignore the integer restriction as if assume that your xj is only greater than equals 0, it may take integer value or real value and solve it by normal simplex method, whether whatever we have done earlier. Now, next step is, does this basic feasible solution, does this optimal basic feasible solution satisfy integer condition? So, we are checking after getting the optimal solution that whether this BFS is integer, satisfying integer constraint or not. If yes, then current basic feasible solution is optimal integer solution and you stop the process. Now, if the current optimal BFS does not satisfy the integer constraint, then find the basic variable having largest fractional part. Please note this one. Then you find out the basic variable having largest fractional part, and once you have obtained the largest fractional part, then use the corresponding Gomodian constraint equation for this variable, which I have written. Write the corresponding constraint equation for this variable. Find the Gomodian slack variable and Gomodian cut for this variable. This we will show whenever we are going through the example for this. So, we are finding the Gomodian slack variable and Gomodian cut for this variable. Then modify the simplex table for optimal non-integer solution. Modify the simplex table for optimal non-integer solution by adding one more row and you use the dual simplex method. Because in the last one, if we have shown here the value of the integer, the value of the basic variable will be negative. So, I cannot solve it by the normal simplex method. That is the reason we are writing here modify simplex table for optimal non-integer solution by adding this one more row and use dual simplex method. Gomodian slack variable will be the initial living variable in this case, and then you repeat the process as we have done earlier. So, these are the basic steps which we will use. Now, let us take this example. We may not be able to finish this example, but let us start this one. We have a problem, maximize z equals 3x1 plus 3x2 subject to two constants. For simplicity, we have taken one simple example and by which we will show you how to the algorithm for IPP works. So, at first you write it in the standard format, that is already it is maximization problem. Maximize z equals x1 plus 3x2 subject to, since both are less than equals type equation. So, introduce slack variables to make them equality. So, 3x1 plus 6x2 plus x3, this is equals 8, and next equation is 5x1 plus 2x2 plus x4, this is equals to 10, and your x1, x2, x3 and x4 are greater than equals 0. So, here your slack variables are x3 and x4. Therefore, in the basis x3 and x4 will go. I will make x1, x2 as 0, then x3 equals 8 and x4 equals 10. So, in the basis your x3 and your x4 will come. So, you are writing x3 and x4. Your b values will be y3 and y4. Cj's are 1, 3, and corresponding to x3 and x4, here it will be 0 into x3 plus 0 into x4. So, you are getting this one. So, these values are 0, 0. Your b values are 8 and 10. Now, write down two rows as usual, that is 8, 3, 6, 8 already we have written, this is 3, this is 6, this is 1, this is 0, and next one is 5, 2, 0 and 1. So, from this original problem you are converting into the standard form, and after converting this one into the standard form you are writing the corresponding equation, corresponding table you are formatting. So, Zj minus Cj if you consider, then minus 1, minus 3, 0 and 0. Here you see Zj minus Cj less than equals 0. It is not satisfying the optimality condition, but x3 and x4 values are integer now. So, we will use the normal simplex algorithm. So, therefore, this will be the entering vector, because maximum negative value occurs over here. So, from here it is 8 by 6 is the ratio, this is 10 by 2. So, obviously, the minimum of these two is this one. So, once the minimum of these two is this one, means your x 2 will enter into basis and x 3 will go out. So, once x 3 is going out, so in that case your pivot element is this one. So, your pivot element is this. So, let us construct the next table where x 3 will go out and x 1, x 2 will enter. So, from here in the table, here now it will be x 2 and x 4, because x 2 is replaced by x 1, here it is coming as y 2 and y 4. CV values are like earlier, that is 1, 3, 0, 0, and here it will be y 2 is 3. So, it is 3 and 0. So, like normal methods, I have to make this one as 1 and this element as 0. So, by doing this one, what we are getting is 4 by 3, half, 1, 1 by 6 and 0. Whereas, this will be 4, 0, minus 1/3 and this will be 22 by 3, this will be 4, this value you will get as 0, this will be minus 1/3, this is 1. So, Zj minus Cj is half, 0, half and 0. So, here if you find your Zj minus Cj, Zj minus Cj is greater than equals 0 for all j. So, optimality condition is satisfied. But if you see here, your x 2 value is 4 by 3, which is non-integer. So, since this is non-integer, therefore, your feasibility condition is not satisfied. So, you have to proceed, or we have to check what to do next. So, what we will do in the next class, we will continue with this example.